Okay. Hope everybody's doing okay. Sometime today, I'll start grading those exams, and I'll post the key. There's office hour this afternoon too, um, and I know some of you wanted to talk about um, doing some stuff in Grace on that, so we can do that during office hour. So come to office hour today if you want to go over that stuff. Today, chapter 8 is in chapter 8 is a chapter where we have to do a lot of grinding through definitions and looking at some things, phase diagrams and so on, that it's almost like background. So in chapter 8, there's not a lot of stuff or problem solving to do. There's a lot of learning. There's a lot of figuring out to do in chapter 8, which is always kind of a grind. So we'll try to get through that today. Does anybody have any questions? Let me make this bigger. 1, 2, 3, 4, 5, 6, 7, 8. Okay. So mostly today is going to be discussing and trying to understand and work with phase diagrams. The first part of this in DeVoe is a discussion about variables. And this is really a question of how do we know either what variables we're going to use to control our system or describe our system. And at first, there's a bit of a discussion about the number of variables that we're going to think about: T, P, N, V. What else could we be thinking about? These are really the 4 that we're going to be concerned about, but some of these are intensive. There's also molar volume, which is of course a combination of these two, and that is an intensive variable. And I think when we first learn about intensive versus extensive variables, there's a sense that intensive variables are better, right? But because they're like the density, they're unique to a substance, which is true in a general chemistry sense, but it doesn't necessarily mean they're better. Because it's necessary to have at least one extensive variable, which I will mention. Okay, so in this chapter, unless and succeeding chapters, unless it's expressly mentioned, we're not going to talk about. We're going to exclude gravitational, surface, electrical, work potentials. The most common one we're going to introduce back in is maybe surface, because it's very important at particular times. But for now, we're going to leave these to the side. And what I want you to do is we think about now a system with no equilibrium, right? If we have no equilibrium and we have phases, and let's call P the variable for phases. So we could have a solid and a liquid and a gas, or one of those, or two of those. Then in general, there will be 3 P variables needed to describe this system, right? So typically this would be something like T, P, and N, for example. P and N and V are not independent, right? So we could specify the volume or the pressure, but for example, it might be T, P, and N. And this is a system where there's no equilibrium going on. So we could have like an open glass of ice water, right? We have water vapor in the air, we have ice cubes in the water, and eventually we're going to just end up with a glass of warm water. So this is not at equilibrium. If we want these to be at equilibrium, we have to impose some conditions. So let's talk about that. Each time we require an equilibrium, this will impose a condition. So for example, if we say T of one phase equals T of another phase, this really fixes temperature and it eliminates a variable from the 3P that I've just mentioned, right? All right. So what this really means is that the P variables become P minus 1. And the P minus 1 is not saying that we have P minus 1 phases. It means that per phase, we're going to lose a variable, right? So if I have a temperature variable, a temperature for the solid phase and a temperature for the liquid phase, and I want them to be in thermal equilibrium, they're equal. So I go from 2 to 1 variable, right? So that's the P minus 1. And this happens for each of them. So what happens is, so we start off with 3P variables, but we're going to subtract 3 times P minus 1 for each of the equilibria we impose. This gives us simply 3 when you do this. So in other words, for an open single substance system, right? So you can think about CO2 or SF6 or H2O. Any number of phases, has at most 3 independent variables to adjust. So if we think about a 2-phase system, we might fix the temperature, right? That's a natural thing to fix. But we could also fix the pressure of the alpha phase and the pressure of the beta phase. Now, typically we would make these the same, right? But whether we make them the same or different, we're fixing them. So if these are our three variables that we're going to, we might adjust the temperature and the pressure of the two phases, which is actually kind of hard, but this is what we could do. What this is going to do is it's going to fix the amount. So it turns out that we need to always have at least one extensive variable to describe the system. And this seems so intuitively obvious, I don't think we think about it enough, right? So if we think about temperature, which is an intensive variable, and pressure, which is an intensive variable, and density, well, we can't simultaneously fix the density and the pressure without allowing the volume to change. So the volume is our extensive variable that's actually implicitly required when we include the density, because if the mass is fixed, then the volume is going to change. If the volume is going to change, then the mass is fixed. So we have to have one extensive variable, right? This is going to be M or N or V in order to describe this system. This leads us to what's known as the Gibbs phase rule, right? The Gibbs phase rule is going to tell us the mathematical restrictions on the number of variables that we can have to describe the system. Okay, so okay, so what we're going to do is we're going to talk about, again, P phases. We have P phases. There's a total of 3 independent variables that we need to describe the system. So it turns out for each phase, we need an extensive variable to describe the system. Okay, so this means we can have 3 minus P other variables, right? These could or should, right? If we need intensive variables, so these could or should be intensive variables. I want to point out that if they turn out not to be intensive variables, we can make them intensive variables by using a combination of extensive variables, right? So that's always what we're going to end up doing. So we have the Gibbs phase rule. The Gibbs phase rule says F, which we call the number of degrees of freedom, is 3 minus P. This is for a pure substance. In other words, we don't have a mixture. F is known as the degrees of freedom, right? So, and we can see F as either the number of independent intensive variables that we need, or the maximum number of intensive properties we may independently vary. Many times it turns out if we think we have more than one property that we're varying, we're actually not, right? So an example of this is the pressure and the volume. So very often we think we're varying them both independently, but of course, if we have a constant volume system, if we have a constant pressure system, then we're holding the pressure fixed, right? Which is really independent variable. We could change that external pressure, but then that's going to change the volume, right? Because they're tied together. So the Gibbs phase rule will kind of always tell us the number of variables or properties that we can actually vary or control, even if we think we're doing more than that. So let's do a simple example that we might be able to get a handle on. So let's imagine a closed closed container with water in it, right? So once we close the lid, if we put liquid water in there, we're going to have liquid water and water vapor above it, right? So let's imagine, remember this has to be pure. So what we're going to do is we're going to get a vacuum, right? And somehow put some liquid water in that vacuum. And we know from freshman chemistry that there's going to be some water vapor coming off the liquid, and it's going to reach some equilibrium pressure. So we have these two phases, P equals 2. So if V is fixed, then the phase rule says F equals 3 minus P equals 1. So there's only one variable that we can change independently, right? That's going to end up being either the pressure or the volume or the temperature, right? T or P or V over N, really, because remember we need, if we specify the amounts, we're going to have an intensive property to play with, right? There's some definitions about this that we call these things. If F equals 2, we call this a bivariant system. If F equals 1, we call this a mono or uni. I guess I see uni more often, univariant. It may be that we can't independently specify anything, right? You may know this is going to be what we call a triple point, for example. This is called invariant. So these are just some definitions we have to get out of the way. So now this seems all very abstract at this point, right? It's just equations and numbers, and it's hard to tie this to what's really important. So let's try to do that now and put this in the context of a phase diagram or phase diagrams, right? Really, our system lives in a 3D space. So for example, this might be temperature, pressure, and volume, or temperature, pressure, and amount, right? Because we need one extensive variable. Now, very typically, we'll talk about constant number of moles. We'll talk about, things per mole. So It may be that we put these two things together to get molar volume, but then that's still a third variable that we're gonna talk about, right? So the full or a full phase diagram is a three-dimensional phase diagram, but we usually look in 2D just because it's hard to think in 3D. Or another way to think about this is it's hard to vary three variables at once. We've already kind of talked about this when we did our total differentials. You know, we often have a total differential that's a function of three variables. And really, it's hard to let three variables vary at once. We want to let one vary and see the response of the other. So that's a very common thing that we're going to do experimentally. So the first thing I want to say as a recommendation is do not try to completely digest 3D phase diagrams immediately. Right? It's too hard. Let's look at an example of a 3D phase diagram from the book. Come on. All right. So come on. All right. So here's the 3D phase diagram. This is going to be CO2. And we have temperature along one axis here. We have volume, actually molar volume, right, along this axis. And then we have pressure along what we would maybe think about as being the z-axis. This is kind of hard to figure out, and it would help if there were some, to me, it would help if there were some shading going on here, right? So here we have, this is all a gas phase. And what you can think about this is really three dimensions, right? So, and actually, if I were to try to shade this, maybe if I just try to kind of shade this the way you would do if you could turn this and look at it in three dimensions, is it would look like this. Right? So in other words, this gaseous area has a kink in it, right? And you can see that in the two-dimensional, right? In the two-dimensional representation here. And we don't really see that in other areas, but in this gaseous, in the gas part of this, the area kind of below the surface that we're kind of seeing here, it's really two surfaces here, right? There's a two-phase coexistence region, liquid and gas. There's a liquid region. There's a gaseous region. There's a solid and gas region. There's a solid region. So what I want to do, this is CO2, and what I want you to do is think that we live, right? We live in areas that are just way down here in this corner in terms of pressure, right? So it's difficult for us to think about this. Now, there's also another representation of this same diagram. So let me, why is this not letting me? Huh, I might have to make a new note. This is weird. Let me add this other diagram down. So here's another one. This is the same, this is also for CO2. But this now is a different area. If you'll notice, the molar volume goes from 0 to 300 cubic centimeters per mole. And this goes from 0 to 3,500 centimeters per mole. So this other phase, the second phase diagram, cuts through the volume region that's just like about a tenth or maybe a 12th of the area here. So it compresses just this lower area, right? And you can see that maybe, right? But it expands this more interesting area, which includes SCF, which is super critical fluid, which we'll talk about a little bit today, right? So this is kind of complicated, right? Okay, good, it gave me another page. Sometimes it doesn't do that. Sometimes when it gets to the bottom with a figure, it doesn't let me add another page. So again, I don't want you to look at these things and try to totally figure out how they all correspond. You should be able to begin to understand how, if we make a two-dimensional slice through these regions, how they correspond. The most confusing thing, I think, here is that we have these things called the triple lines. So if you look what it says here, the dash curve is the critical isotherm and an isobar. So this dotted line is a critical isotherm, right? We haven't really defined what critical means. And this dotted line is the critical isobar, right? So the isotherm is vertical and the isobar is horizontal in a two-dimensional representation. So if you look down at these two-dimensional representations, P versus V, right, then you can see the isobar. And if you look at the P versus T, you can see the isotherm, at least part of it, right? You can't really see it here because what it does is you don't see that kind of change of shape or change of surface in that two-dimensional slice. So these are kind of hard for us to figure out. So what we usually do is we go to a 2D diagram. And depending on what we want to look at, we're going to fix different variables. So we're going to usually look at TP diagrams or PV, VM, right? VM is really what we're doing here is maybe thinking about 1 mole of stuff when we talk about VM versus V. Okay, so let's look at or think about some specific things tying into what we talked about before this, right? If we look at a two-phase area, right? So if we look at our diagrams, this is anywhere where it says L plus G, a liquid and gas area, or a solid plus gas area, a two-phase area, then F is 3 minus 2 equals 1. This is going to be univariant. And once we go to a 2D diagram, right, we're already fixing one of our variables. And that means we can only vary one other variable and stay in the two-phase area, right? In a one-phase area, F equals 3 minus 1 equals 2. And we could move through 2 directions and stay in that phase. Okay. Well, we have some difficulty with what we will see physically under certain circumstances. So, for example, a 2-phase region with fixed VM, this is actually maybe going to give us an apparent molar volume, so or an average. So let's talk about a 2-phase water system where we have liquid water and gaseous water. If we want to just go to a TP diagram, then in our closed system, right? Think about how we're going to do this. Again, I talked about a way that's actually not physically possible, right? But in the end, it doesn't matter. We take a closed volume that's in a vacuum and somehow we put some liquid water in there without disturbing the vacuum, right? That's really actually not how we would be able to accomplish this, right? And then what happens is some of the vapor fills up the area above the liquid until the pressure is equilibrated between the two. Well, on a phase diagram, if we're gonna look at a PT phase diagram, the molar volume is fixed, but the molar volume is the total number of moles of water we put into that system divided by the total volume, right? We have 2 phases. The molar volume of the liquid phase is going to be very different than the molar volume of the gaseous phase. But we don't know what those are necessarily, right? We don't know the amount in each phase as we vary in T and P. The only way we could do this maybe is measure the volume change of the liquid, right? And do some sort of calculation. But in general, if we have a 2-phase system, we're fixing the VM, the molar volume, but that's a gross molar volume, right? In other words, it's some average, and we're going to have to figure out a way to deal with that, and we will. So let me draw a cartoon just to visualize this, right? We have the liquid, we have the gas. If we are adjusting T and P, and actually, if we have 2 phases, right, 2 phases, we have a univariate system. So we get T or P, right? And it's not that they're not both going to change. It's that if we change the T, the P is not independent, right? Because the volume's fixed. Or if we decide to change the pressure, then the volume's going to change, because really how can we change the pressure is by changing the volume or changing the temperature. So we can only change one thing in this system once everything's closed in, right? We can't change N either. The molar volume is going to be constant, but it's an average. So as we change the temperature or pressure, we're going to change the amount in the gas phase and the amount in the liquid phase, right? That should be clear. Which means the molar volume of each is going to change, and this is something we could calculate, right, using the ideal gas law, for example. But experimentally, right, we don't necessarily know what it is. How may we experimentally so this is going to be one of the problems that we want to try to solve using a phase diagram. So let's define some terms, right? Typically, so if we fix the temperature in such a system, in such a two-phase system, we'll discuss the pressure, right? So the pressure at equilibrium is called the vapor pressure. And we know this, and actually we probably have a decent feel for vapor pressure because of our freshman classes, our organic chemistry classes, right? Now, this is whether the condensed phase, we have a two-phase system, one of them is a gas, the condensed phase can be solid or liquid. Technically, whether the condensed phase is solid or liquid, the pressure is called the vapor pressure. But if the phase is solid, it's also called the sublimation pressure, right? So that's just kind of it's okay to call it a vapor pressure, but if it's a solid, it's also called sublimation pressure because that process is called sublimation, right? It's just a little bit more detailed word. So let's see how we could measure this, right? So we have another useful figure. Let me find it. Come on. My iPad must be acting up. It doesn't like to. Why is it doing this? Okay. This is being difficult. So here's how we might measure this vapor pressure, right? Constant temperature, so we have a water bath, right? We put a liquid both in this spherical container, doesn't have to be spherical, but that's typically what we do, right? And also in the U-bend of the U-bend of the glassware. And the reason we do this is to make sure that the only thing in between, the only vapor above the liquid is the liquid, right? So in other words, this is where we have to be careful. And initially, this whole line was a vacuum initially, and then we get some of the liquid in here. So the only thing in between here is the substance we're studying. And then what we have here is air pressure or a controllable pressure, right? It doesn't have to be open. It could be hooked up to something where we can control the pressure. Because what we want to do is when that surface is level, then the vapor pressure, PVAP, inside here equals that external pressure, which I'm calling P air, right? And it's easier, usually the experimental systems are set up to control the P air coming in rather than just dealing with what you have. I mean, if this was a student lab, sure, right? Then we'd have this open to the air and you'd have to measure the height difference, right? And this is really a manometer. But in an experimental setup, you don't want to have to do that. You'd rather dial in the air pressure on the outside to the point where they're level, and then you can say that they're the same, right? You don't want to have to go and do a separate calculation, no matter how easy it is. Okay. So that's how we might measure these systems. Let's talk about fixing the pressure. If we fix the pressure, then T is our variable, and we define the melting point or freezing point to denote the equilibrium between the solid and the liquid. The sublimation temperature for solid to gas, and the boiling or condensation temperature for liquid to gas, right? When we fix pressure, it's usual to define a standard pressure. And this is something that's we have to be careful with. We have to be a little bit new because it's a little bit different than what we're used to at this point. We know about the normal, for example, boiling point or melting point. This is where the pressure is 1 atmosphere. But we know in physical chemistry, right, we don't really use atmospheres, we use bars, and they're almost the same, but not quite. So this is actually called the standard boiling point, melting point, etc., is where the pressure is defined as 1 bar. So what's the difference? For water, the boiling point the normal boiling point is 99.97 degrees C. But a bar is a little bit less pressure, right? So let's remind ourselves, right? 1.013 bar equals 1 atmosphere, right? So a bar increment is a little bit smaller than an atmosphere increment, right? Because we need a little teeny tiny bit more of a bar to reach the same pressure. So that means the water boiling point, if it's a standard boiling point, this is 99.61 degrees C, right? A little bit less actual pressure means a little bit easier to boil, right? Okay, let's talk about the critical point. What is a critical point? So if we have a fixed P, then above a certain temperature, we have a fluid phase, right? So what happens is we have a liquid like density, but a gas like compressibility. And I think this is maybe the best physical way to describe a fluid, that if you were to compare it to a gas, the density would be higher than a gas, but it acts like a gas in the compressibility sense, right? You could squeeze it. If you compare it to a liquid, then it has a liquid-like density, right? Approaching a liquid density, but you can squeeze it, right? Which means you could actually change the density a little bit. So that's what happens above a certain point. And we've seen, let me see where we're at here. If you think about the kind of phase diagrams that we typically look at to illustrate this, this is typically like a water phase diagram. But let's, let me do one more picture. I thought I saved this one too, which is in your book, but it bears explaining. No, that's not what I want to do. Give me 1 second here. Copy, new. Okay, here we go. All right. So before I do this picture, let's talk about the other circumstances, because we could fix the. We could also fix the temperature, fixed temperature, right? Above some P, we also could create this. So we could create this critical phase, this fluid phase at a fixed temperature above a certain pressure, or at a fixed pressure above a certain temperature. So what we could talk about is a critical T, TC, or P equals PC. So we could have a critical temperature or critical pressure. The usual way to do this is to change the pressure. So let's look at this. This is a figure in your book. But again, it's a little bit, it bears a little bit of explaining. Done. It's just not. My iPad's clearly not happy about something. So here's the figure, right? So let's explain this figure first. What we have is we have CO2 in this glass bulb, and we're going to adjust the temperature. But inside the glass bulb, we have 3 spheres of different densities. So sphere 1, the density is about the critical density. Let's call it DC, right? So one of the spheres has a density that's really, really close, essentially the same as the density at the critical point. One has a density less than the critical density, and one has a density greater than the critical density. So that's what those 3 spheres are. All right, so the first picture is the fluid. So we would call this a supercritical fluid. Is that showing up? Okay, that's a supercritical fluid. So right here, this is 1. Right here, this is 2. And right here, this is 3, right? Now, if we lower the temperature, so actually going from A to B, we're lowering the temperature a little bit, right? What happens at a phase transition, we haven't talked about this at all yet, right? But what happens at phase transitions is that the fluctuations in the phases become infinite. This has to do with reversibility. So in other words, what we're really saying, if we talk about something like ice water, let's think about ice water at equilibrium, right? If we're able to maintain this equilibrium, then we know that the amount of ice is not going to increase and the amount of water is not going to increase or decrease. They're going to remain the same. But microscopically, we're getting continual melting and freezing, melting and freezing, melting and freezing back and forth. So the number of these melt freeze events, we can think about melting and freezing events, goes to infinity, right? It's reversible, right? So the way to think about this is that there's like a bazillion of these events going back and forth. And in order for it to freeze, we get a bazillion and one freezing events compared to the melting events. And then it starts to freeze. If we want it to melt, then we get a billion and one melting events compared to a billion freezing events, right? So the difference is vanishingly small, but we're moving in a direction. So does that kind of make sense? The number of events, melting and freezing events. Okay, so that's what's happening here in B, is we're just above the critical temperature. This could be just below the critical temperature. And what happens is the fluctuations in the density are so huge that it looks like a fog, right? Because the light coming through is not being consistently scattered. I don't know if that kind of makes sense. So what happens here, right, is we're just above the critical temperature. So this is 2, but now 1 and 3 are here, right? C, slightly below the critical temperature, right? Slightly below the critical temperature. So it's really hard to see here. And I have to say that one of the things that I found frustrating in 35 years of learning this stuff and teaching this is it seems like nobody can take a freaking good picture of this. These pictures are above average to look at like a critical, supercritical fluid. These pictures are really good, but what you can't really see here in the picture is there's a meniscus here. You can see it if you really look hard, right? And you could probably see it if they had a higher resolution image or looked at a different angle. Anyway, it's really hard to see, but there's a meniscus there. So what we have is 2 phases. So what we have here is we have down here sitting at the bottom is the heavy one. But now you'll notice this one is 2. It's sitting right above, right? It's sitting right above the fluid or the liquid. And this one is sitting slightly below the meniscus, right? And here finally, right, we're well below the critical temperature, so we really have phase separation, right? So now we have 3 and 1 and 2, but 2 is kind of floating. 1 is exactly balanced, and 3 is kind of sinking a little bit, right? In other words, you can think about it as being a boat, right? 3 is kind of like a boat. And anyway, so to me, this really helped to kind of think about what those balls were and to label them, because you can't really tell what they are by appearance. You almost can. That's one thing you can tell in this picture, maybe. All right, so that's a supercritical fluid. It's really interesting. If you know, one of the things I would have done as a student, because I remember trying to do this when I was a student, I had to look in books for pictures of this, right? Because the internet we had the internet, believe it or not. We did have the internet, but not like we have it now. And everything wasn't on the internet, right? Most stuff was still in libraries. So you had to try to find these pictures. It was very time consuming, and then they were crappy. Now we have the internet and the pictures are much better, but they're still kind of crappy, right? They're not as good as you would think they would be. But these, I have to say, these are better than most. All right, so let's talk a little bit about measuring this kind of phenomenon and how we can relate this to the experiment. Because let's say what we're able to do. My iPad's really not happy. I might have to reboot it. Let me find a figure. What we're able to do is we're able to, come on. Boy, I hope my iPad's not broken. That's really not gonna be a good thing. Apologize for this. I don't know of a better way to import this stuff except on the fly. If you do it beforehand, you end up not being able to add stuff. Okay, so what are these? This on the left is a CO2 diagram, density versus temperature. But what we have here is we have, if we relate this to our figures up here, right, A is above the critical temperature. I'm really not able to scroll, so maybe we can do this. So A is above the critical temperature. So here's A out here. We just have a fluid, right? What we have here, if you look at the density, the liquid is on top, high density. The gas is on the bottom. So what we really have in these two separate curves is we're able to measure two different densities, right? So at a given temperature, we have this point and this point. And they're labeled, one's a triangle and one's a square, but they're really hard to see, right? It's really hard to see this. Okay, so B is just above the critical temperature. So B is really close to here too. But C is right here, and then let's say D is here. Okay, so that helps fix what's happening here. So at both D and C, we have two different, we can see the two different phases. We see the meniscus. And if we measure the density of those two phases, then we get 2 points, right? Okay. Well, the problem is it's very hard to experimentally measure the critical density out here. It's very hard to measure this. So how can we do it? Well, it turns out that this line is the average of the two densities. So you can measure either the average just somehow by weighing the system or by knowing the density of the liquid or the gas. And what you do is you extrapolate this out here and you can get the critical density, right? The density, and it's, you can see critical density is pretty close to the average. Now, sometimes this is SF6. Does it have to be? So this is SF6. And sometimes if you really blow this up, you can see this extrapolation doesn't quite match, right? So the solid line is a linear extrapolation, and you see this line starting to bend down, and the actual critical density is here. But it gives you a pretty good idea of figuring out what the critical density is, right? So let's think about another situation where we have a two-phase composition. So let's go back to our closed water system, right? And what we can do here is we can typically measure the pressure, and let's measure the volume, right? So if we have this closed system, let's imagine a glass closed container with some graduations on the side, so we could figure out the height of the volume of this interface, right? Well, if you think about this, what we can do is we can, if we look at a pressure versus a volume or molar volume system, then what we can do is we can add or remove heat. Now, notice I'm not saying temperature. I'm not changing the temperature. So, because if we do this right at the boiling point, right, we're going to have a point where we have liquid over here, pure liquid. And if we add heat, we're going to start boiling it, right? So that's going to be this point A. Or some vapor, right? And we're eventually going to add heat, to where we're going to go to point B. Here's point B, where we're going to have only the vapor, right? All right, so we're going to progress through these points. So what we can do is we can see this is kind of a phase diagram like this, where we have the liquid on the left and the gas on the right. And we might have to take a second to think about this, right? But as the molar volume increases, we're going to get a gas. As the molar volume decreases, we're going to get a liquid. So this is going to be something like 18 milliliters down here. This is going to be something like 30,000 milliliters out here, right? And I'm just kind of using ideal gas law numbers and the density of water, you know, to relate these to molar volumes. You could go back and try to see where I got those. We know that at some point up here, there's going to be a critical point, right? For example, but what we're doing is we're traveling across this space. Well, so what's really happening here is we have a fixed number of moles. And if we have constant pressure and we're putting heat in, then the volume's going to change, right? The volume of this thing is going to change. So what we can do is we could calculate very easily the molar volume, because the number of moles is fixed, and all we have to do is measure the volume as it changes. But the problem is this is a mixture. It's a mixture of gas and liquid. And the question is, the liquid has pretty much a fixed molar volume. The gas has a fixed molar volume, right? In other words, if I come down here, this is going to be the molar volume of the gas. If I come down here, this is going to be the molar volume of the liquid. Once we're in between, we know what the molar volume is, but what's the composition? Just in very simple terms that we're actually not going to use percent, right? In very simple terms, what's the percent liquid and what's the percent gas? Or in other words, it might be really mole fraction liquid, mole fraction gas, right? Percent's just easier to kind of say or think about. How do we do this? Well, we can use, if I can scroll again, I'm really having trouble with this today, right? So let's talk about this a little bit. Let's blow up this region a little bit. We have point A, we have point B. We're going to pick some point in between, which I'm going to call S, right? So we have this line of constant pressure, and we have V over N here, right? Down here, we have Vm of the liquid, because the liquid, remember, I'm going to draw my lines in again just to help us figure out what's going on. Vm of the gas. And in here, we could call this the molar volume of point S, right? Because this is going to be a liquid plus gas region. So how can we figure out the volume? Okay, so the volume at point S, the volume at point S is really going to be the volume of the liquid plus the volume of the gas, right? So in other words, at any time, we can represent this whole volume. And now remember, this volume is going to be changing. So we have more of a piston system like this. We're going to have some liquid down here and some gas up here. And up here is the volume of the gas. And up here is the volume of the liquid. But volume is definitely conserved, right? So we can definitely say that because it's an extensive property. All right. But the volume of the liquid is some function of the molar volume, right? What's the total volume of the liquid? This is going to be the number of moles of liquid times the molar volume of the liquid. right? And the volume of the gas is going to be the number of moles of gas times the molar volume of the gas. And I know what you're thinking. You're thinking, I don't know what these moles are. That's what I'm looking for. But I'm going to introduce these as variables so I can solve for them. Okay. Well, we also know that the number of moles is NL plus NG. So this is something as in physical chemistry, we try to get really adept at, right? We're going to have equations that describe our system, and we're going to have a bunch of variables, and we need to think of clever ways to eliminate variables, right? So we need as many equations as we have unknowns. So if we say the molar volume of S, right, which is the volume of S over the total number of moles, right, because we can't distinguish at that point, this is going to be the NL VML plus NG VMG over NL plus NG, right? So what I can start to do here is I can start, and actually this is not the way I want to do it, but let's think about what we have to do to try to isolate these variables, right? What we're going to end up with, and I'm not going to do it here because I'm running out of time. And frankly, it's good practice to see if you can do this, right? What you get is you get NL times VML minus VS over N. And I'm putting it as VS over N to be more in line with what DeVoe does. I would naturally call it the molar volume of the mixture, but that's not what he does. So, but it ends up reversing on the other side. So let's look at this. Again, let's look at our line because we have point A, point S, and point B. And if we look at what these are, remember that this is Vm of the L, this is Vm of the gas, and this is Vs over N. So this distance here is that VmL minus Vs over N. That gives us that length. And this gives us that length, right? So what we can do if we have a plot, like if we have a plot like this, then we can count up the units. All we have to do is count up the length of those segments in terms of our units. So we can call this L of the liquid phase, L of the gas phase, right? And we get NL times the length of that L, liquid phase, plus NS times the length of that solid phase, right? Or, I'm sorry, and it's gas, not solid. I just can't read my own writing. NG over NL equals the inverse of the lengths. This is known as the lever rule. So where is this going to come in handy? We're going to see, we will use this in many two-phase diagrams to figure out the composition. So anytime we kind of have this bell curve like or concave down region, and it's typically in a pressure volume diagram, but it's not always a pressure volume diagram. We have one phase on one side and a critical point on top, right? Again, if you look at figure 8, 9 in your book, it's not labeling it, but it's there. There's a critical point up at the top. Then we can figure out, as long as we're in a two-phase region, the composition of those, or the composition of each phase, depending on where we are in the volume. So this lever rule is very popular. There's going to be other things that we find out, lots of funny things about these two-phase regions. So let's think about a second. I don't want to get ahead of myself, but it's interesting. Because equations of state usually have problems with two-phase regions, right? So a good equation of state, you can probably have an equation of state that describes a liquid phase. You could probably, it might just be density. D is m over v, right? We might have an equation of state that describes the gas phase, might be the van der Waals equation. But they have trouble in two-phase regions, and funny things can happen mathematically. So this is, let's write this down, trouble. And what we're going to do in these regions is do a Maxwell construction. So it turns out many times that a Maxwell construction plus a lever rule are done together, two pieces that come together to tell us what's going on. And that's actually what we're going to be able to talk about next time. So next time, in the last part of chapter 8, we're going to start looking at some useful things that we can get out of phase diagrams. Phase transition information, composition, and the Clapeyron equation, which is kind of like the most important part of chapter 8 is the end, the Clapeyron equation, which is going to allow us to figure out what phase is stable when, right? And of course, to do that, we're going to use chemical potential, which is really just Gibbs free energy, right? So that's where we're going with that. So if you're able to slog through this material, this lecture, this part of the chapter, the end is pretty useful and profound. And then I think chapter 9 will hopefully, if you like physical chemistry anyway, will be a lot more useful and interesting, because we're going to talk about mixtures. Okay. Does anybody have any questions?
I have one question.
Okay.
So it's just like near toward the end when you said, when you convert Vs over N into the NL parentheses VML minus Vs over Vn. I was just wondering how you got to that point.
It's algebra, right? So the standard professor's response to this is you should be able to do that, right? So you should be able to do that. So what I would say is try to do it, but maybe if you come to office hours today, you can either come to office hours and say, well, I couldn't get it, can you help me? Or you can say, oh, I got it. So this is one of those cases, remember I said that you just have to try it. Sometimes you just have to kind of dive in and see if you can get there, and just play around with the math, and you might end up with like just a rat's nest knot of math that you can't get out of. But maybe it'll work out. You can see basically that you basically need to use an equation to eliminate the n itself, right? So you don't have n in your final equation. But after that, it's basically just a rearrangement. So you can do the multiplication do the multiplication. Notice that effectively what you've done here is you have one variable, right? So the trick here is if you look at the first step you might want to do is multiply both sides by NL plus NG, right?
Yeah.
Well, but that equals N, so don't you end up canceling? You do kind of, but if you leave that N there, now remember what I called this? If you call that VS over N a new variable molar volume of the mixture, then you're not going to your tendency is not going to be try to cancel that out because you've absorbed it into like a new variable, right? And if you do that, it should be doable to do that manipulation. So I actually think that this rearrangement, if once you kind of have that hint, is doable. So it's one of those things that you do it and you get the answer and you feel a sense of accomplishment, and then you can go, then you can go on, right? So it's one of these like things that you can do it, and once you get there, you can feel good about having done that, and then the next one's not as scary because you've done this one. Anyway, that's just kind of what I think. And it makes sense too. It makes sense that that the molar volume that you see is some average, and it makes sense. It makes sense that the further you get this way, the more gas it is, right? And the further you get this way, the more liquid it is. So it makes sense that it should be proportional, to the composition, which is inside the molar volume some way. So it kind of makes sense that we'd be able to extract a mathematical answer from this. Does that help? So I'm basically gently telling you to do it yourself, but you can do it. You can do it. It's a good one to do. So yeah, come to office hours today and we can talk about stuff like this. Okay, any other questions? Okay, I'll see you later. I hope you have a great day.